Hi, my name is Jade. I use she, her pronouns. And yeah, let me get right into helping you with your question. So, what we're looking at here is a Stoic question, basically. Um, we're asking how many grams of NaN3, right? So that's sodium uh, nitride, right? How many grams of sodium nitride will yield 4 gallons of molecular nitrogen gas? So first key thing that'll screw us up is that nitrogen is diatomic. So diatomic molecule, right? So if you just do N, what you'll notice is you'll get an answer that's twice as big as the one you actually want. So that's the first thing we gotta watch out for. So what are we gonna do? Well, first thing we need to do is say, okay, so we have NaN3, right? And that's going to yield probably through some process, unless it's yielding just sodium metal, um, nitrogen gas as part of it. So what I'm going to do is I'm going to say like maybe the equation has some other components in it, but we're not going to worry about that right now. What we're actually going to do is I'm going to do kind of a bare bones approach. So what I'm going to do is say, okay, well, it'll yield nitrogen gas and sodium. I'm just assuming solid sodium. So the assumption I'm doing here would be that this is like some sort of heat decomposition sort of thing like that. If it's a more specific equation, your teacher would give you that specific equation. The process would be the same though. So the first thing we need to do is balance the equation, right? Well, one thing we see is, okay, well, we got one Na and one Na. All right, that's the same. We got 3 nitrogens and 2 on this side, right? Well, that's an odd number, and there's no way we're going to get an odd number by assigning coefficients to this one, right? Can't 2, 4, 6, 8. We can't get an odd number. So the first thing to do is to go ahead and say, all right, let's put a 2 here. Well, that brings us up to 2 sodiums on this side. So 2 sodiums on that side, and 6 on this side. Well, hey, look at that. 2 times 3 gives us 6. So now we have a balanced equation, right? And so now we move into our mystical, magical Stoic line. This is my favorite way to do Stoic things. Start with what you have, right? Okay, 4.0 gallons of N2. What's the first thing I need to do? Well, I want to turn this into grams of NaN3. So we know that when we're moving between species, right? So different species in the equation, we need to go into moles. Why is that? Moles are a counting number, right? A mole is 6.022 times 10 to the 23rd of something. It's a really weird and seems like an arbitrary number. It has to do with the mass of a proton. But long story short, it's the same thing as saying like a dozen of something, right? So if you have a dozen apples, you have 12 apples. You have a mole of apples, you have 6.022 times 10 to the 23rd apples. So we need to turn this into a counting number. We need to turn this into moles. What are we going to do there? Well, the first thing we need to do is turn gallons into, we could turn gallons directly into moles. You're probably going to want to turn it into liters first. So 1 liter is 0.264 gallons, it looks like. So 0.264 gallons gives us 1 liter, right? And that's going to be gallons of N2 and liter of N2. And so then now we're going to cross these out. Okay? So now we're in liters of N2. What's the next thing? Well, at standard temperature and pressure, right? Which your question doesn't give you any specifics, so we're going to assume that it's standard temperature and pressure. If not, you would use your PIVNERT, your PV equals nRT equation, to use the number of moles and the temperature and the pressure the volume and the temperature and pressure to find the number of moles. But in this case, what we're going to do is we're going to say, okay, so 1 mole of gas at STP is going to be 22.4 liters per mole, right? So at STP, we have 22.4 liters per mole. That's our key thing, right? So 22.4 liters of N2 per 1 mole of N2. Now the key thing with that is it doesn't matter what the gas is, right? It doesn't matter if it's a really, really big molecule. It doesn't matter if it's a really small molecule. It's just gonna be 22.4 liters per mole, right? So the liters depend on the number of gas molecules, not the weight. That's a key part of it. And that comes out of the kinetic theory of gases, right? When you derive this equation from like first principles and you use different ideas of logic on that. It doesn't have mass in it anywhere, just counting numbers, right? Just moles. So now we got 1 mole of N2, and now we're getting more into familiar territory, right? So 1 mole of N2, well, we want to change from moles of N2, right, to moles of sodium nitride, right, NaN3. Okay, well, now we just go up and take our coefficients here. This is called the mole ratio. So 3 moles of N2 and 2 moles of NaN3. So the liters N2 cancels, the moles N2 cancels. So now we got moles NaN3, and we want it in grams. So all we have to do now is we just go and pull up our periodic table, and we're going to add together our molecular weights to find our molar mass. And we'll go ahead and truncate that for you. It looks like it's 65.01 grams per mole. 65.01 grams of NaN3 per 1 mole of NaN3. Okay, well, now we cancel out all our units, right? Bam, 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 bam. And so now we have grams of NaN3. So all we need to do is multiply everything on the top, multiply everything on the bottom, and then divide those two. So let's go ahead and do that out real quick. Calculator out here on the phone. So I'll type in 0.264 times 22.4 times 3 gives me 17 in the denominator. And then if I press the 1/x button on my calculator, I'll get a phone that's not listening to me. Doesn't want to listen to me. Okay. Bear with me one moment. There we go. The 1/x will go ahead and take the reciprocal of that, so I can just go ahead and multiply the top now. 4 times 2 times 65.01. And that gives me, as a final result, 29.32 grams of NaN3. So we need that many grams of NaN3 to get 4 gallons of N2 gas, right? Key thing in here is remembering that moles per liter is dependent on the pressure and the temperature, not on the weight of the gas, right? If it's an ideal gas, which we're assuming here, if it was a non-ideal gas, you'd have to use the van der Waals equation, it'd be a whole mess. If it's an ideal gas, which we're assuming here, 22.4 liters per mole. And that'll get you most of the way there. The rest of it is Stoich. And so if you're looking for any more help, or if this my tutoring seems like it's been useful to you, please look me up on Wyzant and Jade D. You can get my details from the Ask an Expert question below, or find me at wyzant.com/tutor/JadePhysChem. I hope that was helpful, and I hope to see you soon. Bye.